Assalamu alaikum class. Today we're going to practice 10 or 20 different types of maths that involve functions, domain and range. The reason I'm not only doing maths is because functions, domain and range, these three topics, they're mostly involving examples and maths. There is not much theoretics that are to be discussed here. So let's not talk and further ahead. Let's jump right into it. Our first math is going to be very easy. It is, let a function f of x equals to 2 minus x divided by, well, let's start off easier. 5 by 2 minus x. Let a function f of x equals to root 2 2x minus 1. And then what do we have? F of x equals to 1 by root over 2x minus 1. 1, 2, 3. These are the absolute basics of domain, function and range, and I'll start with number 1. Now, when we are seeing a function and we see the variable or any variable that is concerned with us, that is of the polynomial of f of x, we first of all see that polynomial and we determine the position of that variable in the expression. In this case, the x is in the denominator of a fraction. And what do we know? The condition on the denominator of a fraction is that the denominator cannot ever be 0. So this expression right here, 2 minus x, this one cannot be equals to 0, because if this whole expression is equal to 0, then it would be 5 by 0, which is undefined. So we definitely can't have that. So for this fraction to be a function, so to be a successful function, 2 minus x cannot be 0, so we can just impose that condition and write this. 2 minus x cannot be 0. This one is the cannot be sign, and then we can just determine x from this, or x cannot be equal to 2. So the domain here is every real number except for 2. So if you want to write the domain, then it's d of f. It is all real number minus 2. As simple as that. And for the range can be all real numbers. RF is all real numbers. Why? Because we can put in any single value can come from this. Except for 0. Except for 0. Any value can come from this except for 0. Why it is not 0? I will explain that just a bit later. Let us just deal with the domains right now. Actually, yes, let's just deal with the domains and leave the ranges for later. Now going on to the second one, this is 1. Is this screen recording? Yes, it is. Okay. For the second one, we see where it is a polynomial of f of x, and we can determine where f of x is. And here, the variable x is inside of a root over, or inside of a square root. And we know what the condition for a square root is. The condition for a square root is that it cannot be negative number. It cannot be a negative number. Why? Because root overs of negative numbers does not exist, and they are termed as imaginary numbers. And let's not get into that, because that's a whole separate conversation. So since this cannot be negative, we can already infer the condition on this, which is going to be 2x minus 1 is greater or equal to 0, because even if this is 0, the root over 0 is 0, so it also can be 0. But it just can't be negative. So it can be either equal to 0 or it can be greater than 0. So from this we can just figure out what x is. 2x is greater than or equal to 1, or x is greater or equals to 1 by 2, right? So from this we can figure out the domain is this x is greater or equal to 1 by 2, then it's going to be 1 by 2 to infinity. Now, if you want the explanation of the brackets here, I can give a very quick one of that. There are three types of brackets generally, and we use all three in domain and ranges. First of all, this one, this, and this. What does this one mean? This one means that if x and y are two numbers, then the domain or range, then the list of number includes x. It includes all the numbers between x and y, and it equals y. So if we illustrate this on a number line, it's going to be that x plus 1, x plus 2, y. So it's going to be x, all the numbers between x and y, and y too. So it means that in this list, x is going to be included, all the numbers between x and y are going to be included, and y is going to be included. And now we move on to the second brackets. What do the second brackets mean? The second brackets mean that only these two numbers are going to be included. So only x and only y. Nothing between them is included. So if we illustrate this on the number line, it is x, y. Here, only x and y is going to be accepted. All the values that are inside of x and y, these are not going to be accepted, and these are not a part of that list. Okay, that's simple enough. Let's go on to this one. First brackets mean that for elements x and y, first brackets mean that for the elements x and y, all of the elements inside x and y, well, between x and y are going to be accepted, and x and y themselves are not going to be accepted. If we show this on the number line, it will be for any number x and y, x is not going to be accepted and y is not going to be accepted, but all the numbers that are inside of x and y, they are going to be accepted, and that is what is meant by this. Now, you may be asking, what are these? This is a combination of the first and of the third brackets and the first brackets. I think you can already guess what it is, but this one, let's just, well, actually, can you see? Oh, I'm sorry, I was drawing without. Well, I'll just explain again. For second brackets mean that only the two numbers that are in the set are going to be included, and everything that is inside them. Otherwise, everything that is between x and y, they are going to be excluded. So only x and y. The first brackets mean that in any two elements x and y, x and y are themselves are not going to be included, and only all of the elements between x and y are going to be included, as illustrated by this. X and y are crossed out, and all of the middle values are contained. Now, what are these last two values? Let me just tell this further. These last two are for any element x and y. This is just a combination of this and this, because this one means that x is going to be included and y is going to be excluded, and all of the elements between x and y, they are going to be accepted. If I illustrate this on the number line, it's going to be x, y. So x is included because of the third bracket, and then every element between x and y is included, but y is not included. And then we go to the opposite case, which is the first bracket is on x and the third bracket is on y. And then if we illustrate this on the number line, if we illustrate this on the number line, for any elements x and y, x is not going to be accepted because of the first bracket, it's not going to be there, and y is going to be there, and all of the elements between x and y, they're going to be accepted. So in this case, the element x is not present in the set, but every element between x and y is there, and also y is there. So these are the brackets. I hope I'll not explain them further because these are pretty easy. But you may still have some difficulty, which I totally respect. Let's go into our main discussion again. We're discussing domains. So we did this, and now for the third one, it's actually just a combination of the first two. We see what variable the polynomial is. It's f of x, so x is our variable. And then where is x? X is in the denominator, but wait, it's also inside of a root over. So we know how to do this individually, but how do we do them together? Oh, wait. Yeah. What was I saying? Yeah. First of all, we looked at f of x. So x is the variable here. We look at the position of x. It's in the denominator of the fraction. So it's simple, right? We just equated that it's not equal to 0. But that's wrong. Why? Because we can also notice that it's also inside of a square root. And we know that for square roots, it's greater than 0. So how do we do this? It can't be equal to 0, and it also has to be greater than 0. What is this? For the answer is pretty simple. We just convert from can be greater than 0, greater or equal to 0. Let's just eliminate the greater from this. So what happens if we eliminate the greater? In this case, it will have to be only greater than 0, because even if it's equal to 0, it will be cut out because the denominator cannot be equals to 0, and if it's less than 0, it cannot be because a root over does not accept negative values. So we just equate it using that. Root over 2 minus x into x minus 1 has to be greater than 0, or we just square each side. 2x minus 1 has to be greater than 0, or 2x has to be greater than 0, or x has to be greater than 1, I'm sorry, or x has to be greater than 1 by 2. As simple as that. What's the difference between this and this? It's that in this one it can be either equal to 1 by 2, and this one it cannot be equal to 1 by 2, it can only be greater. So the domain for this one is df equals to 1 by 2 to infinity. You may be asking, why do we put like the first bracket of in infinity? Because we cannot define what infinity actually is, where it ends. So no matter what number we say, it's not going to be exactly within infinity, or it cannot include infinity itself. So it's quite an abstract concept, so we put the first bracket for this. And 1 by 2 is the first bracket here because it cannot be 1 by 2, it can only be greater than 1 by 2. So 1 by 2 itself is not included, and we know that when something is not included but the elements between them are, it has the first bracket. Okay, so that's the basic discussion, and this is like the simplest, as simple as you can go. Let's put out some harder ones. What can I do for the harder ones? Yeah, let's go with this one. For number f of x equals to root over x squared. Let me just alter the equation. Where is my calculator? Oh my goodness, I can't find it. Oh, it's here. Okay, let's just put this one in, I suppose. 3x minus 7x squared. Oh wait, no. 3x squared minus 7x plus 2. First of all, we simplify what's inside of the square root. How do we do that? We just use our calculator, of course. If we use our calculator, we can find that the values are x1 equals to minus 1 by 3 and x2 equals to minus 2. So the factors are x plus 1 by 3 and x plus 2. So it can be actually simplified as x plus 1 by 3 or x plus 2. There's actually no meaning to this step because we actually need these values, not these ones, but I'm just using it to explain it. Now, we use a method here called the jump rule. This might be complicated or it might not be complicated, but I find it pretty easy. At first, no matter how many factors we have, we're going to take them and factor them all to 0. So if we take the solution and factor this, we get our original values minus 1 by 3, minus 1 by 3, and we get minus 2. So, actually, let me just minus 2 and minus 1 by 3. Okay. Now, what is the condition on root overs, if we can remember again? The condition for root overs is that it has to be greater or equal to 0. So our numbers here, they have a dot on them because they're included in it. So x has to be greater than minus 1 by 3. X has to be greater than minus 2. But wait, that doesn't make sense. How can a number be greater than both of them at the same time? Here comes like a twist because these two both numbers can be either positive or they can be negative. So the first situation is x is greater than both of them, and the second situation is x is smaller than both of them. Because two negatives make a positive, right? But this is, I feel like it's too cumbersome, and I think it's a more simpler solution is to just use this. Now, we took our two numbers on the number line, and now we draw some more values. Like, let's just put 0 here, let's put 1 here, let's put nothing. We don't need to put anything. Let's put minus 3 here, okay? Now, we have took two values here. The values that we took, we're just going to put a line over them. So I put a line over minus 1 by 3 and I put a line over minus 2. So now what happened? What happened is that in the number line, we divided the section, the whole number line into 3 parts. The part where it's greater than 1 by 3, the part between minus 2 and minus 1 by 3, and the part that is smaller than minus 2. Now what's the benefit of doing this? The benefit of doing this is that we can just figure out, we can just put any value in this and we can figure out which one contains the solution of solution of f of x or solution of x. For example, if let's input any number that is greater than minus 1 by 3 into this equation. Let's put 1, for example, a very simple value. What do we get? X plus 1 by 1 plus 1 by 3 and x plus 2. 1 plus 2. Okay. Well, generally factoring, when doing equations like this, we generally want to put the variable x instead of the specific value because it's going to be much faster that way, since you can still substitute any value you want. Okay? Got that. Now we first of all put a number that is greater than minus 1 by 3, so it's going to be 1. In my calculator, it shows that it is valid. So, where's my marker? I forgot where it is. Anyway, since I can't seem to find... Oh, there it is. Okay. Oh, let's just do it with the red one anyways. So I found that this and this side, it accepts all of the values that I gave it. For example, root over x plus 1 by 3 and root over x plus 2. If I put 1, it gives me a value. If I put 3, it gives me a value. If I put 11, it gives me a value. So, from testing out or substituting the values of x that is greater than 1 but minus 1 by 3, we can see that it satisfies the equation. So, this part, all of that part from minus 1 by 3 to infinity, that will satisfy the equation itself. And now, we test the second part, which is between minus 2 and minus 1 by 3. So what's the value between minus 2 and minus 1 by 3? Let's just put minus 1 by 5. So minus 1 by 5. Minus 1 by 3 minus 1 by 5. Okay, my minus 1 by 5 is actually it's greater than minus 1 by 3. So if we put a fraction, minus 1 by 5 minus 0.2. So what's the value that is smaller than minus 1 by 3? It's minus 1 by 2. I'm so sorry about this. It's minus 1 by 2. I messed that up. Or we could just put minus 1. What am I doing? It's so simple actually. So I put minus 1, I put minus 1 by 2, but in both cases I see that it gives me a math error. So I can clearly see that the numbers that exist between minus 2 and minus 1 by 3, they are not, this one is, of course it's not working. They are not applicable. It's a huge cross. They're not applicable in this case. So again, we try out our third quadrant or third division, which is the numbers that are smaller than minus 2. They are minus 3. So let's put minus 3 as an example value in it. I get a value. If I put minus 5, I also get a value. If I put a value minus 8, I also get a value. So from testing out, we see that we always get a value when we put values of x that are smaller than minus 2. So what can we infer from this? From this we can infer that the domain for this are the places that values of x exist. So since this is from minus 2 all the way to infinity, it's going to be minus infinity to 2. Why did I put the first bracket? I put the first bracket because it can be either equal to 0 or it can be greater than 0. So Since there is also the equal part, I put the bracket in this. Union minus 1 by 3 to infinity. Why did I put the union? It's just a way of saying that there are two domains and the combination of them is the actual answer. Combination of them is the actual answer. And why did we put the third bracket in minus 1 by 3? Because minus 1 by 3 is included in this case. So that's pretty simple, but here's where the neat part comes in. Let me just draw the previous number line again. It's minus 3, minus 2, minus 2 is the value, so there's a line, minus 1, minus 1 by 3, that's also the value, so there's a line there, 1, 0, 1, okay. So what's the neat part about this is we can just test out one single segment. For example, I put in my calculator, I put the value of the numbers that are greater than minus 1 by 3 in my calculator, and it showed that there are values in it. So from the jump rule we can infer that since this one has a value, this one does not have a value, and this one has a value. Basically it just alternates. So if there are 3 divisions, the first division there is a value, then the second division there isn't a value, and the third division there again is a value. And if it occurred in any case that, for example, x is a value and y is a value, and there's 0 in the middle, and there's 0 in the middle, then if this value didn't have any answers, then this one would have an answer and this one wouldn't have an answer. So if I gave you any equation and you substituted any value and it came across that all the values that are greater than y all the way to infinity, you just put any 2 or 3 values in and you found that they're incorrect or there's a math error, then this one doesn't satisfy the equation. And then alternating, since this is across the next division, which is between numbers between x and y, there are going to be successful values, or there are going to be the applicable values of x, and then again the next division, which is from x to minus infinity, they're not going to be part of the equation. So the neat part about this is we can just draw a number line, separate the segments really quick, and just figure out one segment, and then we can just alternate them. I'll show you another one, and I'm gonna do this one really fast. Do I have board space? I do. Okay. 5 f of x equals to 1 by 3x squared minus 7x plus 2. So from the previous one we know that x1 equals to just these two values, so I'll just draw a number line. It's minus 1 by minus 2, minus 1 by 3, let's put 0, let's put minus 1, and let's put minus 3. Okay. Let me just put this equation in my calculator. 1 by root over 3x squared minus 7x plus 2. I'll just show it in the calculator. I just put this value in, and then I just press a random value in it. For example, minus 1. Minus 1. Okay? Yes. Okay, my camera cut out, but I'm really sorry about this thing because everything is correct. I just forgot to put a plus in this. There's going to be a plus here, so I'm going to edit this, of course, but there's going to be a plus here instead of a minus. I'm sorry about that. Now moving on, we're going to, if I can just find my marker again. Yeah, there it is. Let's solve this again. If we put minus, the values actually are going to be 1 by 3 and 2. We just got that from the calculator. So we map them out on our number line. So we put minus 1, we put 0. Well, actually no. We put 1 by 3, we put 1, we put 2, we put 0, and we put 3. The only numbers that are important here are actually the two numbers between the two numbers of the two solutions of x. The rest of the numbers are just sample numbers that we use to input it into the calculator. Now, I'll just do this really fast. I'll just write this whole equation in the calculator. 3x squared plus minus 7x plus 2. Okay. So, if let's say I put 3, there's a value for 3, there's a value for minus 2, but there isn't a value for 1. So since I found this is going to be correct, and this is going to be wrong, and this is going to be correct. So the range is from 2 to infinity and domain is from 2 to infinity and from minus 2 to 1 by 3. Here, why is it not for in bracket? Because this is in the denominator, it cannot be equal to 0. It can only be greater than 0. So since it is not equal, it cannot include these numbers 1 by 3 and 2. So the domain for this is minus infinity to 1 by 3 union 2 to infinity. That's basically the jump rule. I probably explained it with a lot of fluff, but that's the basic premise of it. Now let's move on. Let's put another really simple one. F of x equals to, let's say, 4 squared minus x squared. So, applying for a squared minus b squared equals to a plus b into x, a minus b, 4 minus x and 4 plus x. So, what are the values? The values are going to be x equals to 4 and x equals to minus 4. So, x equals to minus 4, x equals to 4, and there's going to be 0 in the middle. We just put this into our calculator. 4 minus x and 4 plus x. We just put this and we put in just one segment, the value of one segment. So let's put 5, which is the segment of this. I put 5 and I got a math error. So this segment is crossed out, this segment is okay, and this segment is again crossed out. And since this is within, this has no denominator, so it's greater or equal than 1. So the range is going to be, the domain is going to be minus 4 to 4, including that. Let's just test it if it takes minus 4. And it does. If I put minus 4, it's 0, and if I put 4, it's also 0. So the domain is this. So that's very easy actually, it's just a matter of getting used to. So I hope that's the jump rule cleared and finished properly. Now let's tackle a bit more of a difficult problem, I'd say. If f of x equals to root over x divided by root over, let's x plus 1 divided by x minus 2 into x minus 3. Now, what do we do? This is difficult, right? Because normally we only have the denominator, only have x in either the numerator or the denominator. So how do we do this? Well, surprisingly, it's not that much different. We just factor all of this. We just put it in the number line, and this is 2, this is 3, and this is minus 1. Since these are not equal, they're just going to be accepted. Well, actually for denominators, I don't think you even need the jump rule, because for denominators, there's only a single value that is not accepted. So we can already infer that x is not equals to 2 and it's not equals to 3. We don't need any jump rule for that. Now, what happens to this one? We can just set these two aside and figure this one out. It's minus 1, so there's only one segment. The numbers that are greater than minus 1 and the numbers that are smaller than minus 1. So let's put 2 here and let's put 0 here. We write the given expression into the calculator exactly how it is. We put minus 2, it's another, we put 0, 0. Yeah, so since we put minus 2 or minus 3 or any number that is smaller than minus 1 and we didn't get a result out of it, so obviously this part is going to be the correct answer. Now again, since root over is greater or equal than 1, so it also accepts minus 1 as its answer. Or actually, I'm sorry, it actually doesn't, because numerators also can't be 0, or otherwise they're just 0 by 1 is 0. Root x plus 1 is minus 2 and x minus 3 plus 1 0. No, I'm correct. I don't know why I spaced out, but yeah. Mine was correct. It's greater than 0, greater or equal than 0, so minus 1 is also an acceptable value. So, what is the domain in this case? This one is interesting because we really can't unite it all together. If we just write it informally, it's going to be minus infinity to minus 1 and union 0 to 2. Union minus 1 to 2, union 2 to 3, union 2 to infinity. Yes, this is the correct answer. Yeah, I know it looks very complicated, but trust me, it's really easy. Unit 3 to what does this one mean? This one just basically means that every number from minus infinity to minus 1 is correct. And then union minus 1 to 2 just means that every value from minus 1 to minus 2 except for 2 is correct, which we have because every number except for 2 and 3 is an acceptable number. And then from the this one means that from 2 to 3, from 2 to 3 besides 3, like besides 2 and 3, all the numbers between 2 and 3 are acceptable. And then this one, the last one, means that except for 3, all the numbers from 3 to infinity are acceptable. So if we really boil this down, this one just means this part. This one means between the decimals between 1 and 2. This one means the decimals between 2 and 3. And this one means all the numbers from 3 to infinity. So that's really the main part of it, and that is our more difficult expression done. And now let's figure out our last domain of the day, which is something that involves log. Let's start with log 5. Okay, log 5 minus x. Sure. So what do we know about the condition of log? A condition of log or natural logarithm, which is also known as log, is that it cannot be 0. It cannot be any number, cannot be 0, and it cannot be any negative number. So the condition for long is 5 minus x has to be greater than 0 because it does not accept any other values, or x has to be greater than 5. Right? Or 5. Or x is smaller than 5. So what is the domain? So 5 minus x has to be greater than 0, or x is smaller than 5. Let's just put that in and see if that is correct. X minus 5, because that's minus 5 is a value that is obviously lower than 5. Minus 5, it has a value. Minus 0, it also has a value. So this one is correct. And now f of x equals to ln a minus x. Oh, let's put 5 minus x and 5 plus x. Sure. I don't want to really figure this out using the very hard way. We learned this at 9.2 of our logarithmic exercise book. It's that the range, the domain of this is always from minus 5 to 5. Regardless of this is the pluses in the denominator or the numerator, the domain is always from minus 5 to 5, excluding, or let's say if it's, you can just test out if it's excluding or not just by putting this in, putting the values of minus 5 and 5 in the given expression. 5 plus x and 5 minus x. So let's put minus 5 in. It gives me a math error. Let's put 5 in. It also gives me a math error. So these minus 5 and 5 values, they're not included in it, and only the numbers that exist between minus 5 and 5, they're applicable for this. So the first brackets check out, and this is a solid domain. It means it's correct. Now let's put a more interesting one, which is f of x equals to ln 5 plus x and 5 minus x. Well, no. Actually, this is something that involves ranges. And I'm going to explain ranges in 10 minutes. Let me just bear with me. Let's put sine. Yes, sine. Sine x plus 1. We know that the acceptable values for sine are all real numbers. No matter what real number you put in, sine is always going to have a value. So the domain for this is all real numbers. This is something you actually have to memorize, I guess, because it's just a well-known fact. If you try to determine, it's just going to uselessly take you more time in the exam. And we all know that time is a very, and I mean very important facility. And let's put, I guess, well, for any of the logarithmic, not logarithmic, the trigonometric ratios, it's all of them are going to have the same domain. They're going to have the domain of all real numbers. Okay. Now we pretty much discussed the domains of all of the essential ones as far as I know. Now let's dive into the ranges. This is more exciting actually. Let's dive into the ranges from the very beginning. Okay. The first one was I suppose it was something like 1 by 2x plus 1. The second one was root over 2x plus 1. The third one was 4x equals to 1 by 2x plus 1. Okay, so 1 by 2x plus 1, what's the range in this? Actually, to find out the range, we can just find out the inverse function of a function. The inverse function of a function tells us the domain and the domain of the inverse function, and it tells us the range of the original function. So by finding out the inverse function of any function, we can find out the range of this. So let's just try and determine the inverse function. Let y equals to 2x, 1 by 2x plus 1, or we just multiply it, 2x plus y equals to 1, or 2x equals to 1 minus y, or x equals to 1 minus y by 2y. So, what's the condition of y here? Obviously, it's just that y cannot be 0 here. So the domain for this one is y cannot be 0. This is just a very easy one. So y cannot be 0, and since this is the function, inverse function of this function, so it means that the domain of this function right here is actually the range of this. So since we got that the domain is not equals to, it can be any number not equals to 0, so the range for this is Rf equals to all real number minus 0. Okay, that's as simple as that. For this one, we can do the same. Y equals to root over 2x plus 1, or y squared equals to 2x plus 1, or wait a second. I'll just come right back. I'm having a bit of confusion. I'm sorry for the cut again. What were we saying? We were saying that the inverse function of the original function shows the range of the first function, because the domain of the inverse function is at the actual range of the first function. So here we can see that there are no conditions on x, so it must be that the domain here is all real numbers, so the domain of here is all, so the range of the original function is all real number. But there is a bit of a exception here, because we can clearly see that this will never input any negative values. For example, if we put 0, it gives us 1, and if we put minus 1, there is no value. Okay? And if we put 1 by 2, it gives us root 2. So it will never give us any negative value. So we can just cross out every negative value, and we see that this one will give us the range of infinity up until from 0, including 0 up to infinity. I know this one was a bit of a, what do you call it? A bit of a cornball, but it is what it is. This one has a bit of an exception, and it's a 0 to infinity. Now going to this one, what's the, let's find out the inverse function of this. 1 by 2x plus 1 is 2xy plus y equals to 1. Well, actually, it's a square here, so it's going to be squares. No, it's okay. It's fine. Or y squared equals to 2x. Oh no. Or 1 minus y squared equals to x equals to 2y squared. So what's the condition on this again? The condition is that it won't be 0. So here the condition is also that it cannot be 0, and since there is a root over, we know that root overs never give us 0. So here it's gonna be excluding 0 up to infinity is the range of this, and the range of this is including 0 up to infinity. Okay. Now, let us look at the logarithmic equations, which are 5x plus 1. For logarithmic, we know that if you put in any number whatsoever, we will always get a value. So the range of logarithm numbers is all real number, and for sine and cos, let's say we put 1 by x. We know that sine has a condition that sine is greater or equal than -1, and it is smaller or equal to -1. So the range will always be from -1 to 1, and for cos it is also the same. The ranges of sine and cos will always be from -1 to 1, and for tan can be any value. Tan is the range for tan is also infinity. The domain for tan is infinity, and the range for tan is also infinity. Okay. Tan 5. So tan 1 plus x is infinity. So for sine, cos, and tan, the domains for these are all real number, and the ranges for sine and cos is from -1 to 1, and the range for tan is all real number. Okay. Now we go to ln. Ln is also actually the same as this one. Ln is also all real number. The range is from all real numbers, and then what do you have? Well, actually that's pretty much it for the ranges. Well, I know the range one was very unclear. My brain is also actually very foggy, but that's pretty much it. Log has a range of all real numbers. Sine, cos have a range of -1 to 1, including -1 and 1, and tan has a range of all real numbers. Okay. Now we will go on how to verify onto equations. Okay, onto function. I'm sorry. Onto function. What are onto functions? Onto function is basically that the set of which the range of elements is equal to the codomain is called onto function. For example, if we say let x be a variable and codomain be r minus 0. Okay. Now, which one is the correct onto function? Let's put number 1 is f of x equals to absolute of x, f of 2 equals to f of x equals to 1 by x, 3 equals to f of x equals to x squared. Let's put these three for now, okay? Now, the easiest way to find out what the correct answer here is to look at the exception, or the number that has been excluded from the codomain. Here, the number that has been excluded from the codomain is 0. So it means that in the ranges of these, well, in the domain, in the ranges of these, it cannot be 0, okay? So now our question is, which number, if we put as 0, yes, So the question now is, in which function, if we put the result 0, there won't be any function at all. Or we can look out for which functions we put the number 0, there is a range. The functions which, if we put input 0 and we also get a range which is successful, those are not the answers, because the codomain here has been specifically mentioned that it cannot contain 0. So if the range of a function contains 0, so it contradicts the codomain, right? And then it is not an onto function. I know that seemed like a lot of blabber, but we can just verify it. For example, if we put f of 0 here instead of x, then it's also modulo 0, which is 0. So we have 0 as an element of y. But it has been said that 0 is not an element. So this one is incorrect. And then if we look at this one, f of x equals to 1 by x, then f of 0 here is equals to 1 by 0, which is undefined. So 0 is not an element here, 0 has been excluded, so it matches with this one. And again, if we look at this one, if we put f of 0 right here, then it gives us a 0 square, which is also 0, so it has 0 as the element of the range, which is also incorrect since it does not contain that. So our answer here is this one, f of x equals to 1 by x. That's the easiest way to do it, but if we want to do, let's say, a bit harder way or a bit of the more general way, we can verify it by this. What's the codomain? It's the all real numbers minus 0. But in our first case, we get that if we put f of, let's say, minus 2, we get absolute minus 2, which is 2. So, and if we do this for any number, we'll see that we only get positive numbers. So our domain, our range here is from 0 to infinity, only positive numbers. But this has all numbers from minus negative to negative. But in our first case, we are not getting any minus numbers. So the range here does not contain all of the elements of the codomain. So this is not the answer. In our second case, let's say f of 2. In our second case, let's just put f of minus 2 equals to 1 by minus 2. This is clearly a minus number, right? And then if we put f of 2 equals to 1 by 2. So here, whatever number we put in, there is a number corresponding to that, and if you put negative numbers, we will get negative numbers. If you put positive numbers, we will get positive numbers. So this one has a codomain of all real numbers except for 0, because there is no 0 in denominators where which x exists. And then it's the same story for this one. If we put f of minus 2 here, then it squares minus 2 and it gives us 4, meaning it will never give us a negative number, so it has no negative number, so the range here is from 0 to infinity. So it does not contain